So, what is an algorithm? An algorithm is a step by step set of instructions to solve a problem. Three things are always true about every algorithm. There are three properties of every algorithm. One, it has a clear starting point. Two, it has defined steps. Three, it produces results every time. Remove any one of those three, and what you have is not an algorithm. What you have is a bug waiting to happen. Let me show you what I mean. You walk into a shop, you insert your card into the POS machine. In milliseconds, something happens inside that machine. Most people never think about what that something is. So now let me show you what happens. The POS machine reads your card. That is step one. Step two, it sends your card details to the bank. The bank checks your balance. The bank sends back an approval or a decline. The POS machine prints your receipt. These steps, that is an algorithm. Every step, there, there are there are five steps, and they have a clear start. The process has a clear start. There's a defined process, and there's results every time. Now, what happens when one step disappears? For example, the bank never checks your balance, but the machine approves every transaction. Money that is not there gets spent. That is not a feature. It is not a glitch. It is a bug. And that brings me to the first standard every algorithm must meet. That is correctness. So a correct algorithm produces the right result for every possible valid input. If an algorithm is not correct, it is a bug. So we are going to come back to this statement in every single topic in this series, because correctness is not an option. You do not ship an incorrect algorithm and call it version 1. Okay? So the second standard is efficiency. Two algorithms can be correct. Both produce the right answer, but one takes 10 steps and the other takes 10,000 steps. The difference between a recycler view that scrolls smoothly and the one that janks, an endpoint that responds in 40 milliseconds and one that times out under load. The difference between these two sets of algorithms is efficiency. And we measure it with two things: time complexity and space complexity. Time complexity is how many steps does this algorithm take as the input grows. Space complexity is how much memory does this algorithm uses as the input grows. N here is the input size. So for example, if the input size is 500 contacts, N is 500. If we have 500,000 contacts in a contact app in your phone book, the N there is 500,000 contacts. So as N grows, T of N, time complexity, and S of N, space complexity, tell you whether your algorithm is going to hold up or fall apart. Why does this matter right now? I want to give you a perspective that most data structure and algorithm courses skip completely. The developers interviewing at top companies, say Google, Microsoft, and Meta, They are not tested on algorithms because algorithms are academic. They are tested on algorithms because the product these companies build serve billions of users. At that scale, the difference between O of n and O of log n is the difference between a server farm and a data center, between milliseconds and minutes. You are not building for billions yet, but your users are using low-end devices, TechnoSparks, Infinite Hot. They have 2 gig of RAM and a slow data connection. An inefficient algorithm on a low-end Android device does not just make your app slow, it makes your app unusable. So your users will uninstall your app and they may never come back. Now, this series I am doing exists because developers deserve to understand this at the same level as anyone else in the world, right? So, the three things that we have looked in today is that an algorithm is a step-by-step set of instructions to solve a problem. It has a clear start, a defined steps, and a result every time. So in part two of this, we're going to do linear search and binary search, and there will be a full code walkthrough. So you will see exactly how the time complexity and space complexity play out in real Kotlin code.